This week we're going to be talking about heat gain and loss, and specifically how that relates to energy efficiency and the building envelope. The building envelope, if you remember from your reading, is the outline of the house and where it touches either the earth or the air. So it includes our roof or ceiling. If we see in our second story, part of our roof is the same as the ceiling, where it's sloped to the right, and part of the ceiling is flat. Also, any walls that are between the inside and the outside, and any openings that are in those walls, such as doors and windows. And then, of course, the flooring that is part of our foundation if we have a basement, or the walls if we have a basement. So if we have a crawl space, traditionally we don't worry as much about insulating the walls and the floor of the crawl space, but we want to insulate the floor between the crawl space and the space where we live, which is often referred to as habitable space, and it's also referred to as conditioned space. So conditioned space is any space that we as human beings want to control the heat and humidity of. So typically we want to keep it in what's often referred to as the comfort zone, where it's somewhere between the lower 60s and upper 70s. Often 68 to 72 is considered the ideal comfort zone. So in this image that we see here, we do have a basement that could be considered conditioned space. The fact that we're seeing the green kind of teal color underneath the slab and on the edges of the concrete walls towards the outside indicates that this is an insulated space. Also, the fact that the basement does not show insulation between the basement and the first floor indicates that that would be conditioned space, as opposed to the crawl space, which I pointed out earlier to the left, where we see insulation in the floor between the space that people are in and the crawl space. And then up above, we see an attic space to the left of the room that's on the top floor. And that is unconditioned space. So that would be a space used as storage typically. But the space where people are has insulation in the walls, in part of the ceiling there, that is congruent with the plane of the roof, and then in the flat part of the ceiling. Other examples that aren't shown here are garages. Garages are typically unconditioned space. Because much of our discussion will involve basic thermal performance concepts, also referred to as thermodynamics, we want to briefly review some key definitions. They were in the book, but we just want to make sure that you're completely on board. You might remember some of these also from any physics classes you might have taken in high school or college, but there have been some changes in definitions in recent years. So a quick review makes sense, just to make sure that we're all on the same page. The main way that heat transfers is through conduction, convection, and radiation. In the image that we see here, we have a wood stove. So there's a fire inside the stove. The heat from the fire is heating up the stove itself. The teapot sitting on the stove is getting heat transferred by conduction. Conduction is always going to be touching. Convection is heat that is transferred through air. So the cat that is on the shelf above is getting some convective heat as the air rises. And there's radiant heat, which we call radiation. Radiation in this sense, radiant heat, is not the same as radiation that we often hear about, that is X-rays, gamma rays, things like that. So radiant heat has no negatives to it. It just means that the form of the heat is waves, similar to light waves. Matter of fact, there's a reason why light and heat are often in conjunction with one another, and it's because they travel on the same waves. So if we look at the man reading the paper, he's getting radiant heat from the side of the stove, and that radiant heat would actually be going in all directions, even though it's only shown to the left. His feet and legs would be warmed by that, and the paper that he's reading, the newspaper, would get radiant heat. Now, because he's blocked his face with the paper, he would not be getting radiant heat on his face or on his chest, just like the back of the chair would not be receiving any radiant heat. So the back of the chair is going to feel cooler. Now, the fact that the man is sitting in the chair means that his body heat is going to radiate as well as conduct into the cushions of the chair. So that's something to keep in mind as well. When we get back to the cat, because he is radiating in all directions from the stove, the bottom of the shelf would actually be getting some radiant heat as well, and eventually all the fibers in the shelf would be conducting heat. So the heat of the shelf would be from some convection, the air heating up around it, but also radiant heat, that radiant heat conducting through the shelf until it reaches the cat. The cat's tail should be the warmest thing because it is getting some direct radiant heat. It's not shielded by the shelf, as well as, I've mentioned, that convective heat. As air is heated, it rises. We'll talk more about that on another slide. Often the three forces, as I outlined in the previous picture, are at work at the same time transferring heat energy. In this image of a pan of water that's boiling, the pan is getting heated by radiant heat from the fire, where the fire is literally touching the pan. There would be conductive heat. The heat of the pan conducts. Metal is a very good conductor, and so the heat is moving around through the material quite easily, and we see some heat going up the handle. And if this were a very good conductor, a metal handle, the person who's holding on to that handle would get burned by that conductive heat traveling up. Inside the pan itself, the water that's in there, when water gets heated, and the way that water holds on to heat and moves it around is the same convection forces that we saw with air. It's showing some kind of a loop that's happening in there, because as water heats, it tends to rise, and cooler temperature water is denser and falls. The same thing happens with air. Again, there's another slide a little bit down the road that will discuss this in more detail. So again, here we have radiant heat, convection heat, and conductive heat all in the same place. The other things to keep in mind with heat transfer, and we always refer to heat transfer, is that nature is looking for equilibrium. So if something is hot and something is cold, that heat will try to move towards the cold, so that ideally everything is the same temperature. That's the concept of equilibrium. So something warm, something cool, the heat will transfer to the cool side. The opposite sometimes can seem to be true, such as if I touch something that feels cold to my touch, it feels like the cold is being conducted to me, but actually what's happening is the heat of my fingertips is being transferred into the cold item until it reaches equilibrium, in which case it no longer feels cold. My fingertips and the item that it's resting on are the same temperature. As I mentioned, heated air moves upwards. It's less dense. The image of the hot air balloons should be a reminder of this, that there's a buoyancy that happens when air is heated. It takes up more space, it's less dense, and because it's rising, there is a vacuum that occurs, a negative air pressure, and that will bring in cooler air from a lower height. When we start talking about the building envelope, these concepts will be important to keep in mind. The main sources of heat gain, there's 4 sources of heat gain and one that's both heat gain and heat loss. The sun. When the sun shines, we get solar heat gain. The second source of heat gain are occupants. So people and animals, anything that's living and has a temperature above the standard temperature, warm-blooded animals, that is to say, we generate heat. So this little thermal diagram is showing that a person tends to be warmest at their core and cooler at their extremities, but each person is generating some heat, which is why if you have a party and a whole lot of people come over, it tends to get hot in the house and you feel like opening up the doors and windows. A third source of heat gain is appliances. So this is an important thing to keep in mind because it's less common for houses, but for commercial buildings, internal heat gain from appliances and electric lighting are the main source of heat in a building. Most commercial buildings, high rises, actually run air conditioning 10 months out of the year in downtown Portland because there's so much heat being generated from all the people that are in the space when it's during business hours, all the computers, the copiers, the printers, the cell phone chargers, everything that's plugged in tends to create heat as well as running itself. The last thing is air infiltration. So air infiltration refers to air that's sneaking through the building envelope, either through large cracks or small cracks. And air infiltration is a big way that we get heat loss more than heat gain. Now, if it is the summer and it's a hot day, if there's a lot of air infiltration between the interior of the space and the outside, we do get heat gain happening through the walls. But typically what's happening is that we are losing heat from inside the conditioned space to the outdoors. Now, again, remember, it's heat transfer, so we're either gaining heat or losing heat. The idea then, just to reiterate some of these concepts, is that building materials are either going to be conductors or they're going to be insulators. Conductors are items that transfer heat very effectively, And insulators are things that do not transfer heat easily. So if we see this diagram to the right of a house that has been photographed using infrared to see where heat loss is occurring, we see the redder coloring in windows. As I mentioned, windows are a big source of heat loss in a building envelope, but we also see it on all the wall studs. So you might recognize that wall stud concept that we looked at last week of the framing. We also see the top of the top plate and the bottom plate of some of these walls. And our least amount of heat loss is at the bottom of the first floor and up at the roof. That to me is indicating that there is insulation at the second story between the attic space and the ceiling of the second floor. Things that conduct heat most easily are metals, as I've mentioned, glass, and insulators are materials that resist the transfer of heat. Wood is better than metal, but it still can conduct. Concrete is better at insulating, but it still can conduct. Some of the best insulators are trapped airspace and also insulation. If we look at the image to the left, we see that the R value, which I'll talk about in a future slide a little bit more, the R value is a measure of resistance to heat transfer that through the metal stud, so that C shape is a metal stud as opposed to a wooden stud, that we have conduction happening there, whereas in the middle where that sort of zigzaggy shape is, that indicates insulation in the wall cavity. And so we have less heat transfer happening where the studs aren't.